So the final experiment this semester is going to be investigating yet another type of chemical reaction that we talked about way back in first semester, and that's a redox reaction. And we know from our discussions in the first semester that a redox reaction is going to be a reaction where electrons are transferred, right? So we have something that is gaining or something that is losing electrons. So if we look at the reaction that we see up here on the top of the slide, this is an example of a redox reaction. So we have zinc metal reacting with copper nitrate. When those react, those form zinc nitrate and copper metal. So effectively what we're doing is we're trading one solid with another, right? We're trading zinc solid and copper dissolved to get zinc dissolved and copper solid. Okay, so that's our redox reaction. Now we know that this is a redox reaction if we look at the oxidation numbers of each of the elements in the compounds and atoms that are up here. So we know that if it's an atom by itself, it's going to have an oxidation number of 0. Nitrates, the charge on a nitrate polyatomic ion is -1, so copper has to be a +2. The zinc on the right-hand side is +2, and the copper is going to be 0 because it's by itself. Now we could go in and assign oxidation numbers with the nitrogen and oxygen inside the nitrate, but really we don't need to worry about that because those elements in these chemical compounds are not changing charge, okay? But what we really want to pay attention to is the sets of atoms that are actually changing charge. So we can draw an arrow from the zinc 0 to the zinc 2+, and an arrow from the copper 2+ to the copper 0. And those two arrows that I draw there, those are going to indicate my half reactions. So zinc metal on the left-hand side with a 0 charge turns into zinc with a 2+. Now, if we have zinc 0 going to zinc 2+, the only way zinc can become positive from being neutral is if it gives away electrons, if it loses electrons. And we know from last semester, Leo says Gur, losing electrons means it's oxidized, and then the other reverse of that is gaining electrons is reduced, right? So copper 2+ is going to turn into copper solid, but the only way that we can get rid of that +2 charge and go to a 0 is if it accepts 2 electrons, if it gains 2 electrons and is reduced. So Leo says Gur. Losing electrons is oxidized, gaining electrons is reduced. So these are two half reactions. And if we add up these two halves, then we get the overall process, the overall net reaction that actually takes place. And the overall reaction is basically zinc solid reacts with copper 2+ ions to form zinc 2+ solid and generate copper solid in solution, okay, or copper solid at the bottom of the solution. So this is our overall reaction. Now, if we toss all of these things together in one beaker, what we're going to see is the zinc solid is going to dissolve, the copper metal is going to form a brownish solid on the bottom, and that's really going to be the end of the story, okay? However, if we're careful about how we set up this reaction, all right, what we can actually do is harness the transfer of electrons that's happening up here. In this reaction, zinc has to give away electrons, copper has to accept electrons, gain those electrons. So if we're careful about how we construct our chemical reaction, we can actually harness those electrons. We can actually generate current, all right? And so we can do that by creating something called a Daniell cell, and that's what we see down here at the bottom. Now, in this Daniell cell, we've got basically our half reaction split into two different beakers, okay? So on the left-hand side, we have our zinc half reaction. On the right-hand side, we have the copper half reaction. Now, those half reactions are connected by two different channels. One is going to be by a voltmeter, all right? And the voltmeter is going to carry electrons through the outside here. The other thing we need to do is complete our electrical circuit by connecting the solutions, and we connect our solutions by using a salt bridge. Now, a salt bridge is basically a piece of filter paper that we've soaked in a particular solution containing ions, in this case potassium and chloride ions for this picture. Now, what we have in this process is we have kind of I like to think of it as a 4-step process that takes place. Step number 1 is going to be the half reaction, if we zoom in here, the half reaction that takes place at this electrode on the left. The very first thing that needs to occur is a zinc atom, a solid zinc atom, needs to give away 2 electrons. That's step 1. And when the zinc atom gives away those 2 electrons, it's going to form zinc ions in solution. Okay, so that's kind of step 1 that happens over here at the zinc anode. Okay, now step 2 is those electrons are going to move through this external circuit, pass by the voltmeter, so we're going to kind of watch the electrons go by recording a voltage, and then those electrons are going to move down into the copper cathode, and that's where step 3 happens. In step 3, those 2 electrons actually come out and get intercepted by a copper 2+ ion that's floating around here in solution in the vicinity of this copper piece of metal. So the copper 2+ accepts those 2 electrons and forms copper solid. Okay, so the zinc anode, this piece of metal over here in step 1, is slowly dissolving. The copper cathode over here is slowly getting bigger as this process occurs and occurs and occurs. Okay? Now, one of the things that's going to happen is, over the course of time, more and more of the zinc anode is dissolving. We're going to be producing zinc 2+ ions in solution, and more of those. On the right-hand side, we're going to be consuming copper 2+ over on the right. Now, if we stopped there and only had those 3 steps, the reaction would end very quickly. Because you'll notice in solution, on the left we have sulfate ions, on the right we have sulfate ions. Those solutions help to keep the charge overall in the solution neutral. Okay? But the solution on the left is producing more positives, the solution on the right is producing more, or is losing positive charge. So we need to find a way to balance out the charge. And that's where our 4th step comes in. And the 4th step is the movement of ions in this salt bridge. What you'll notice is in that salt bridge, we have a piece of filter paper soaked with ions. The chloride ions are going to move over towards the left to basically neutralize or balance out the extra charge that's generated, the extra positive charge that's generated from the zinc 2+ ions. The potassium ions in the salt bridge are going to move in the other direction. They're going to move to balance out the fact that we've lost positive charge because the copper 2+ ions have formed copper metal. All right? And so the movement of ions in the salt bridge is really step 4. Right? And that helps to equalize the charges present in the solution, and most importantly, it keeps the reaction going. Okay, so we have a complete electrical circuit where those 4 steps are all happening. So the zinc is releasing electrons, the electrons are traveling through this external circuit, the copper 2+ is accepting the electrons, and then the ions in the salt bridge move to balance things out. So those 4 steps all happen, and I've broken them apart into 4 steps so we can appreciate what's going on, but in real life, these are all happening really simultaneously. Okay? So we're going to be building these different batteries here in lab, and that's really what a battery is. It's a device, much like this, that's going to have 2 half reactions separated such that we can put something here in the flow of electrons, in that stream of electrons, and power it, right? So our cell phone battery may look a little bit different, but the basic idea is what we see here. Okay? Now, when we think about these batteries that we produced, we're going to be measuring the flow of electrons and indicating kind of the extent of the reaction by measuring a voltage using a voltmeter. Now, as we go through and test different kinds of batteries, we're going to see that different batteries come about, different voltages come about from different batteries, which have different types of materials in these solutions. Now, as we look at these different types of materials, we always have to measure voltages by looking at 2 different points. And one of the things that we're going to be doing is using the table of half-cell potentials on page 45 in your lab notebook. And that table of half-cell potentials is referenced to a particular point, a particular half reaction. And the half reaction that we're going to be referencing these voltages to, is the standard hydrogen electrode. All right, and so by definition, the standard hydrogen electrode is 2 H plus ions reacting with 2 electrons to form H2 gas. So this is our reference point. Much like for mass, our reference point is the carbon-12 atom. This is going to be our reference point for electrochemical measurements, the standard hydrogen electrode. Now, one of the other things we'll play with in this lab experiment is how concentration affects the voltage of our cell, and we can describe how concentration impacts voltage by looking at the Nernst equation. And the Nernst equation for the zinc-copper battery, which is what you see here, the Nernst equation for that battery is shown down here in the second box. So E is equal to 1.10, so our standard voltage for this type of battery, minus 0.05916 volts over 2, the number of electrons transferred, times the natural log of the zinc 2 plus divided by the copper 2 plus concentrations. Okay, so you'll be using the Nernst equation as you kind of think about some of the things that are happening in the various parts of this lab. Okay.